Hey everyone, welcome to Magnitude. This is Moinak Dasgupta and today we have came to the fourth part of the semiconductor series, and today we are going to discuss about the different types of semiconductors. On my previous videos I have already described that what are semiconductors, conductors, insulators, and even the free electrons, holes, energy bands, and many more things. So if you have not watched that video, then please watch those videos. I will give the link in the description box. And if you are new to our channel, then please subscribe to our channel and hit the bell icon to get the latest updates of our channel. So not wasting much time, let's begin. So let us first understand that how the semiconductors are divided. Firstly, the semiconductors are divided into two types. One is intrinsic and the another one is extrinsic. The intrinsic semiconductors are the pure semiconductors. So these are the pure one. Okay. And the extrinsic semiconductor is known as the impure one. So you might have a question that why we are using impure semiconductors. So we are using extrinsic semiconductors a lot as compared to these intrinsic semiconductors because the extrinsic semiconductors have the more power of conductivity as compared to the intrinsic semiconductors. So we will discuss this thing as we move forward towards the video. And again, this extrinsic semiconductor is divided into two types. One is P type and another one is N type. We will have a detailed discussion of each of these types. So now in case of intrinsic semiconductors, that means the pure semiconductors, we know that generally the semiconductors are made up of tetravalent atoms, means the atoms which have 4 electrons in its valence shell. So what happens actually, that suppose we take silicon, because silicon is one of the best example for semiconductors. So let us take silicon, and silicon has 4 electrons in its outermost shell. So up to this we are clear. Next, what happens next? This silicon is the electrons of this silicon is bonded with the adjacent atoms of other silicon. So they are getting bonded, and this bond is a covalent bond. Covalent bond means the sharing of electrons. So when the temperature increases, means when the temperature increases, this covalent bond will break, and when this covalent bond will break, then this electron will come out and it will come here. So what will happen when this electron will come here? Then here will be a vacancy, and this vacancy is known as hole, because we know that the deficiency of electron is known as holes. So here on one hole will be formed, and here one free electron will be formed. So these two things here, this one is known as holes and this one is known as free electron. So up to this we are clear. And next, these free electrons and these holes, both of these two things are known as charge carriers. So what happens in case of intrinsic semiconductors? Generally we have the number of electrons, the number of free electrons, we represent the number of free electrons as n. The number of free electron is always equal to the number of holes, and we represent it as P, because holes are represented as P. So number of free electrons is always equal to number of holes in case of intrinsic semiconductors, and it is equal to the total intrinsic carrier density. Ni means intrinsic carrier density. So this is a very important property, and it is only valid for intrinsic semiconductors. So what happens in case of intrinsic semiconductors? We have to depend on the natural cause, because it is only possible when the free electrons will be created and the holes will be generated only when the temperature will increase and the covalent bond will break. So in intrinsic semiconductors, the conductivity is literally low because you have to depend on the natural cause. So now we will understand how extrinsic semiconductors work. So now let's talk about the extrinsic semiconductors. The extrinsic semiconductors are the impure semiconductor. So you might have a question that why should we learn this impure semiconductor although we are having a pure semiconductor? I have already given you that answer that in case of extrinsic semiconductors, the power of conductivity of the semiconductor is much higher as compared to the intrinsic semiconductor. You will also find this thing in some different examples, such as we all have seen gold ornaments. But do you ever think that these gold ornaments are not really made up of pure gold? Yes, these ornaments are not made up of pure gold. We add some impurities to the pure gold, and after that we make the ornaments because it makes the ornaments much stronger. Same thing happens for the semiconductors. We add some impurity and make extrinsic semiconductors, and this helps for the conductivity and it increases the conductivity of the semiconductors. So we have now learned that we have to add some impurity, but the process of adding these impurities is known as doping, and doping is a very important term in semiconductors. This is doping. So if anyone asks you that what is doping, doping is nothing but the process of adding impurities. The process of adding impurities is known as doping. So now you will have another question. Now your question is that we know that we have to add some impurities, all right, but what type of impurity should we add? Okay, I am giving your answer. We will add generally two type of impurities in case of semiconductors. One is pentavalent impurity and another one is trivalent impurity. Means either we will add pentavalent or either we will now add trivalent impurity. So one is pentavalent impurity and another one is trivalent impurity. So now you will have a question that what is pentavalent? Pentavalent is nothing but we are adding some atom which have the 5 electrons in its outermost shell. And what is trivalent? Trivalent means we are adding those atoms which have 3 electrons in its outermost shell. So I will like to give you some example of pentavalent and trivalent. For pentavalent atom you can take antimony. Yes, antimony is a very good example of pentavalent, and we generally add antimony as an impurity also. And for trivalent we can add boron. Yes, boron is a very good example. And also we can add indium. Correct, indium is also one good example of impurity that we generally add in pure semiconductors and make it extrinsic. Now I will give you a very beautiful example by which you can understand that how these extrinsic semiconductors have more power of conductivity. So let's move to that example. So here I have taken two examples where one side I have doped the silicon lattice with trivalent atom, and on the other side I have doped the silicon lattice with pentavalent atom. So I have defined this impurity with X in both the sides. Now it is a time when we have to keep our full focus on this trivalent impurity and this pentavalent impurity. What happens in case of trivalent impurity? Actually, we see that the last shell of this impurity has 3 outermost electrons. So the 3 outermost electron will bond with the adjacent silicon atoms present on each side, and one will be empty. This vacancy of electron, we know the vacancy of electron is known as holes. So this vacancy will be known as hole. Now, in case of pentavalent, what will happen? Pentavalent will have 5 outermost electrons. So here the 4 electrons will get bonded with the adjacent atoms of silicon, and the rest one, means the last one, the 5th number electron, will be remain free. So this one is known as free electron. This one is known as free electron. Now what will happen? In case of intrinsics, we have seen that in case of intrinsic, we have to increase the temperature, then the covalent bond will break, and then only the holes or the free electron will be generated. But in case of extrinsic, you see that when we add impurity, then already by default only one hole is created in trivalent case and one free electron is generated in case of pentavalent. So this thing proves that already in extrinsic it is much easier to generate these charge carriers. So just to keep one thing in mind, that these holes are positive charged. So these holes are positive charged and the electrons are negatively charged. So one thing we can say from here, that positive means P. So when we add trivalent impurity in any of these lattice, then this type of semiconductor material is known as P-type semiconductor. And when we add pentavalent impurity, that means one electron will be extra and it is negatively charged, so it is known as N-type semiconductor. Negative, so N for negative and P for positive. So one more important thing that is very much important to know in case of semiconductors, that is in case of P-type where holes are extra. So in that case, in P-type, holes are the majority charge carriers. Holes are the majority charge carriers. And in N-type, one electron is extra. So in case of N-type semiconductors, the electrons are the majority charge carriers. So if in this case the holes are the majority charge carriers, then obviously the electrons will be minor. And in this case, if the electrons are the majority charge carriers, then obviously the holes will be minor. So this was one of the most important concepts where we used to understand what is P-type and what is N-type. So from now onwards, we will not say that this one is doped with trivalent, this one is doped with pentavalent. We will directly say that this is a P-type material and this is a N-type material. So after we have understood the different parts of semiconductor, there lies one of the most famous law in semiconductor, that is mass action law. So let us understand that what mass action law says. Under thermal equilibrium, means when the temperature is constant, under thermal equilibrium, the product of the free electron concentration, means the product of free electron concentration and hole concentration, means the product of free electron concentration and hole concentration, is always equal to the square of intrinsic carrier concentration. So let me write the mathematical form, it will be more easier. So what it says, the product of free electron concentration. So free electron concentration, we represent electron concentration as N. So I have written N. So product of free electron concentration and hole concentration. So we represent hole as P. So the product of N and P will be equal to the square of intrinsic carrier concentration. So intrinsic carrier is represented by Ni and it will be square. So this one is a very important formula through which we can use this formula in various numericals which we have in the semiconductors, because we have to sometimes get the value of the number of electron concentration or number of hole concentrations. So this formula is very important. And one more thing, the intrinsic carrier concentration is a constant term. So this law is known as mass action law. So if you have any doubt regarding the full video, then please mention your doubts in the comment section, because I am going to end this video right here. And if you like this video, then please hit the like button and also share this video with others. And if you have not yet subscribed to our channel, then please hit the subscribe button and also hit the bell icon to get the latest updates of our channel. You can also follow us as magnitude.mt in Instagram to also get the updates of our video. So thank you everyone for watching this video.